information security. So why am I working on subjective logic? Because it can be used to model trust. That's computational trust. And trust is an important element in information security, so that's where that fits in. But I also apply subjective logic for Bayesian reasoning, so that's another research interest. So before working at Oslo University, I worked at QUT in Australia and at another research center. And I have a master's in information security from London and a master's in telecommunication from NTNU in Norway. And I worked as a telecoms engineer for many years before I did my PhD. Okay, so the tutorial today is about subjective logic. And first I will explain the representations of subjective opinions. Those are the arguments. It's belief, basically, how belief is represented in subjective logic. And then with those opinion arguments, many types of operators can be designed. So the input arguments are opinions and it produces an output conclusion, which is also an opinion. And by applying these operators, we can establish formalisms for computational trust, like trust transitivity or trust fusion. Like if you ask two people about an opinion about the same thing, and they say different things, how can you combine those two pieces of advice? This becomes trust networks. And then subjective logic can also be used for Bayesian network modeling. So that becomes Bayesian reasoning. And by combining trust networks and Bayesian networks, it becomes subjective networks. So the general idea of subjective logic is take binary logic, for example, where the variables must have Boolean values, true or false. But instead allow the variables to have probability values. Okay? Then that's probabilistic logic. And extending this by expressing levels of uncertainty about the probabilities, and also allowing ownership of probabilities, not just saying the probability of variable blah is this. You also have to ask, who believes that the probability of blah is that? Maybe somebody else believes probability to be something else. So multiple agents can have different opinions about things. Then it becomes very subjective. So by extending probabilistic logic, then with uncertainty and subjective ownership, then that becomes subjective logic. This is not so easy to see, but this is just a simple example of a few probabilistic logic operators. Let's take the binary logic operand AND, okay, which is normally defined as a truth table. In probabilistic logic, is simply the product. And if you input either probability 0 or probability 1 into the product, you can populate the AND truth table of binary logic. And similarly with OR, it's code product. If you input probability 0 or probability 1 into the code product of probabilities, you can then populate the truth table of binary logic OR. Simple as that. So you don't need to have the truth tables as axioms. You can instead just use some probabilistic formulas. Modus ponens is a very simple formula as well. And also modus tollens becomes a little bit more complex, but you can still populate the truth tables of modus ponens and modus tollens by using these simple probabilistic formulas. And where you input probability 0 and 1 as arguments and outcomes, the rightmost column in those truth tables. And the advantage, of course, of probabilistic logic is that then you can have continuous truth instead of just Boolean truth. And another advantage is that you don't need those truth tables as axioms. Instead, you can define the binary logic operators in terms of these probabilistic formulas, which then becomes a replacement for the axioms, for the truth tables. Okay, enough of probabilistic logic. A little bit over to different types of probabilities. You all know the discussion between the frequentists and the subjectivists in the statistics and probability or AI communities. Let's say flipping a coin. If you flip it a few times, you can work out the frequentist probability of flipping that coin. And it represents something physical because you have observed the outcome of flipping the coin. Whereas if I ask you the question, did Oslo shoot Kennedy back in, was it 1963? And people have some opinions about it. And they might say, yeah, probability 0.7, maybe. But it doesn't represent the frequentist probability, because you cannot count how many times Oslo shot him and how many times he didn't shoot him. It's actually a state of mind. It represents mental states in people's head. And not a frequentist probability. And some people actually think the probability of the coin sits somewhere inside the coin. Of course it doesn't. Probability always sits in your head. Nowhere else. Also in the case of flipping a coin, and in the case of subjective probabilities. So we want to be able to represent the difference between these types of probabilities, and that's possible with subjective opinions. Opinions apply to variables of various domains. So a domain is simply a state space. And it can be binary. If the situation in models is like a light switch, which can be on or off, then it's a binary domain. And the variable can take two values, which is on or off. But you can have ternary domains or larger domains. Any size works, really. Let's say you split the weather in 3 weather types: sunny, rainy, or overcast. It's just a convention. Let's say the weather consists of 3 types. Then you have a ternary domain. Or if you have an urn of 3 colored balls, black, yellow, and white, let's say, then it's like 3 possible outcomes when you pick a ball from the urn. And then it can be so-called hyperdomains. So now let's take the colors of the balls: red, green, and white. Okay, 3 different colors: red, green, and white. If I'm colorblind and I pick a ball, I can't see the difference between red and green. So I see this ball. Well, it might be red or it might be green. I don't know, but it's definitely not white. I know that. I can tell from how bright it is. So then my observation is then, although I know the domain has red, green, and white, for me, this was an observation of red or green, but I don't know which. So if you add this possibility that you can actually observe red or green, but you don't know which, then it becomes a hyperdomain. So let's say these dotted lines around the values. Now here is x1, x2, x3. But if you don't know whether it's x1 or x2, you can say, well, it's x1 or x2, but I don't know which. So if you add these possibilities into your domain, then it's called a hyperdomain. Yeah, so this is just what I already explained, a larger set of the hyperdomain. So you probably know the power set of a set. The power set of a state space consists of all the subsets of the set, including the empty set and the whole set itself. Okay. In subjective logic, we use something called the reduced power set, denoted R, calligraphic R. And in the reduced power set, we take away the empty set and we take away the whole domain. Because we cannot observe the empty set and we cannot observe the whole domain. There is no observation which consists of, I picked a ball. Yes, this is a ball. No, it's not a meaningful observation. It's a ball is not a useful outcome. And if you pick a ball, I didn't pick a ball. I missed one. No, it's not an observation. So the reduced power set contains all the subsets of the domain minus the empty set and the whole domain itself. So here are the three possibilities, not just binary, and then a larger domain, and also the reduced power set of the domain. And underneath we see a triangle, and we see a tetrahedron, or a pyramid, and a dot inside the pyramids and the tetrahedrons. And at the bottom you see, not very visible, but it's a beta probability density function, and then it's a Dirichlet in the middle probability density function, and the one on the bottom right is a hyper Dirichlet probability density function. The dot in the triangle is actually a representation of an opinion about a binary variable. A dot inside the tetrahedron is a representation of an opinion about a ternary variable that can take three different values. And the beta probability density function, which you cannot see, is an equivalent representation of the dot in the triangle. And the Dirichlet, which is also hard to see, is an equivalent representation of the dot in the tetrahedron. And this hyper-Dirichlet is an equivalent representation of something which cannot really be represented in a tetrahedron. But anyway, it can be represented as a hyper-Dirichlet. So the representation of a binomial opinion then is, it's denoted with an omega. Okay? And the subscript indicates the value to which it applies. And then it's a tuple. And the tuple consists of belief mass, this belief mass, or which is basically belief mass to the complement of the value x. Then there is the uncertainty mass, and then the last one is the base rate of the prior. And there is some additivity, like in probability calculus, the sum of all probabilities must be 1. Here, the sum of belief, disbelief, and uncertainty must be 1. So this is a bit similar to the differences, so that you know about the differences. So you have belief, disbelief, uncertainty adds up to 1. So if you want to say, I don't know, you can assign 0 belief mass, 0 disbelief mass, and uncertainty mass equals 1. So now this becomes a valid argument, as an input argument to some reasonable. You can say, it's allowed to say that. But you also have the base rate, which is a prior mention. And now comes the triangle again, because now belief, disbelief, and uncertainty, these three parameters. Okay. This is a barycentric coordinate system. if you take this equilateral triangle, okay, and you take a distance from the left side edge to some place, and the distance, which is then the distance is the belief mass, and the distance from the right side edge is the disbelief, and the distance from the baseline to this point is the uncertainty mass. So you can now put the point anywhere, put that point anywhere inside the triangle, and the sum of those distances from the edges or from the baseline is always 1. That's the fundamental principle of the barycentric coordinate system. So there you get geometrically, you represent geometrically the additivity of these 3 parameters. And we can do more stuff geometrically. The base rate, or the prior, you can just put it as a point on the baseline. And you can't really see it, but the line from the top, which joins the base rate point, is called the director. And now make a line in parallel with the director from the opinion point to the baseline. This is the projected probability of an opinion. So although an opinion contains lots of uncertainty or whatever, if you really want a probability, there you have it. Okay, it's a scalar probability, the projected probability. So this is a geometric visualization of how to derive the projected probability based on the line joining the top and the base rate. But there is, of course, a mathematical formula, which is simply the belief mass plus the product of base rate and the uncertainty. So here's an example. If you take the probability 0.4, 0.2, 0.4, so what's that? Let's take the distance from here to here is 0.4, the distance from here to here is 0.4, and the distance from the right edge to the point is 0.2. So this is the opinion point. And the base rate is 0.9, so that's over here, 0.9 on the baseline. So draw a line in parallel with that director from the opinion point down to the baseline and get here. And this value is 0.76. You can visually or geometrically compute the projected probability. Here are some typical opinion types. If you put the point in the right-hand corner, then that's equivalent to binary logic, true, Boolean true. Put the point somewhere on the baseline, then that's equivalent to classical probability. And put the point at the top of the triangle, that's a vacuous opinion, which represents ignorance. Put it somewhere inside the triangle. It has some evidence and some uncertainty. So it's just a general opinion. It can be triangle. It has a bit of evidence and a bit of uncertainty. So it's a general binomial. And the equivalent representation of a probability. This is back in the classical tradition of statistics, the probability density functions. This is a beta. So the formula for the beta is this formula there. Don't worry about that. The beta has 2 parameters, alpha and beta, and these are the strength parameters. And the strength parameters can be split up into observations. Observation of, let's say, flipping a coin. There are 2 observations, heads or tails. Let's say R represents the number of heads, S represents the number of tails you have observed. And then there is the base rate, the prior, which for a coin, you could say base rate is 0.5. And then is the W, which is the non-informative prior rate, which is equal to 2. So this is a philosophical question. What should the non-informative prior rate be? But in general, the rate should be 2, equal to 2. So then, these alpha and betas in the beta probability density function can be then replaced by, of course, observations and prior. So let's say you have now, or can have Earth with black and white balls, and you wonder how many black or how many white are there, and you pick 3 balls, 2 of them happens to be black, and 1 of them happens to be white. And here, in this case, the base rate is 9, which is not really representing the order of just 2 colors. So let's say the base rate is 0.9. Then you get this probability density function. And the expected probability, now it's called expected probability because the probability is now the variable, actually, the variable of the beta, is 0.76. So the same value as we had for the binomial opinion. So these are equivalent. Okay? This is an equivalent representation of that point in the triangle. Okay. So here you see it. There is an adjective mapping between those 2 representations, and it's very simple. Just simple formulas there. You can go both ways. And here is the demo I'll show you. There is actually an online demo of subject project you can access. So this is a Java applet, but I know modern browsers, they don't like Java applets unless they actually sign to the certificate. And this one is not signed. So your browser will say, no, stop. Warning, warning, dangerous, dangerous, don't do this. So you have to actually specify an exception. You have to specify the URL and say this is okay, this URL is okay. Every time you get a new browser, it's a new way of doing it, so I don't know how to do it. Okay, so here's the opinion point. Okay, and I can, if I then put it at the top, I put the opinion at the top. Then we see the equivalent probability density function, which is flat. It's a uniform. Okay, so it's a uniform. And let's say we pick the balls from a node, or we pick points, we get more information. And we see how the beta changes, and it becomes, eventually it should become an infinitesimally narrow and infinitely high peak Dirac delta function. But this applet isn't perfect, so actually it's not infinitely high and it's not infinitesimally narrow. So this is then equivalent to a traditional probability. But we forgot about base rates. Here's the base rate. It's called here atomicity, but forget about that. So the prior of the base rate actually influences the probability density function. So if you are completely uncertain, then you see it has great influence on the probability density function. But if you are very certain, then the base rate doesn't matter much. Because you have an infinite amount of information, so the base rate doesn't count. Let's say you have an urn of black and white balls, and you say, oh, the base rate should be 0.5, because there are 2 possible colors. And you start picking balls, and you say, actually, there are 90% white balls and 10% black balls after picking 1,000 balls. I know that, pretty sure. So then you have figured out that despite the base rate of 0.5, you now know the relative frequency of the balls. You don't need the base rate, because you have enough evidence. And another way of representing opinions can be through qualitative or fuzzy categories. Because humans are not very good at expressing opinions in terms of numbers. For example, did you see that thing happening over there? Can you please express it in a probability or like an opinion? People don't know what's that. But if you say, it was very likely that actually this happened, or that this is correct what I saw, it's very likely. How confident are you? I have high confidence, or I have low confidence, or I have no confidence. So we are typically educated in expressing levels of likelihood, like probability, but expressing levels of confidence about the likelihood is more so. That's where people are challenged. But this is exactly what subjective opinions represent. You can now express levels of confidence about the probability. So you can say, I have a probability 0.5, but I'm not very confident about it. So who uses this? Actually, in the military intelligence communities, they use this. Because here comes a spy from the field, and he says, hey, I spoke with some people who's a member of Putin's friends. Sorry for using some specific examples, if there are Russians among you. And he said that they plan to withdraw from Ukraine or something like that. With how likely is that? Well, it's like it's 0.9. But how confident is he? Well, actually, he was a bit drunk at the time, so maybe he was just talking some rubbish. So I'm not very confident in this. So actually, they use likelihood and confidence to represent statements when they make intelligence analysis. And how does this then apply to opinions? You take a matrix of likelihoods and confidence, and as you see, it's skewed. One is skewed to the right, and the other one is skewed to the left. Why is that? Depends on the base rate. Let's take another example. Let's take the case of tuberculosis of a random person in New York. Not many people have tuberculosis these days, but maybe still some people might have it. So the base rate of tuberculosis in New York is very, very small. That means the table should be skewed to the right. Even more than the leftmost table here is skewed to the right with base rate 1/3, but let's say the base rate is 0.001, then it's really skewed almost in parallel with the left side of the triangle. And then you see that there are many rectangles or many fields which are actually outside of they don't overlap with the triangle. So what does that mean? That means you cannot express these types of opinions. They don't correspond to anything. And what would that be, for example? Let's point at a person through the window of the hotel. So we can say, do you think this person's got tuberculosis? Yes, I think so. Okay? And how confident are you about that? I have no confidence. I'm completely uncertain about it. But I think the person's got tuberculosis. That would be an opinion up here. Okay? Very likely, but totally unconfident. That's a nonsense opinion. It doesn't correspond to anything. Okay, so you're the people, the experts. There should be no expert who gives such an opinion because it's meaningless. Whereas, if you point at a person on the street and you say, do you think this person's got tuberculosis? I don't think so. Hardly anybody in Europe has got tuberculosis, so no, I don't think so. How confident are you about it? I'm not confident because we need to take a test like this before we know, so I'm completely non-confident, completely unconfident. That's a meaningful statement. Because now imagine that this rectangle, this parallelogram is skewed all the way to the right, so that its left side overlaps with the left side of the triangle. Then this top little field here up in the left corner. Okay, I'll go over here. That is this little field here in the rectangle, in the parallelogram, would actually be inside the triangle. There it would be. So it's a meaningful statement to say that somebody on the street, you don't think that person's got tuberculosis, but you are not confident about it. Because before you apply a test, when you take a blood test and get the results, then you are confident whether or not the person is with tuberculosis. So it all depends on the base relation, whether these kinds of statements make sense or not. Okay? So that's what I explained. So we can have multinomial domains. Of course, not just black and white or heads or tails. And then the opinion representation looks a little bit different. Still an omega. And now the variable x, let's say, can take many different values. x1, x2, x3, x4. And the opinion now is the tuple of a belief mass distribution. It's not just one belief mass, but it's a distribution of belief mass over all the possible values of the variable. x1, x2, x3, x4. So now we don't need this belief because, let's say, belief mass applying to x2 is like disbelief for x1. So basically, it's basically a distribution. That's what it is. But still, we have the uncertainty mass, and we have the base rate now distribution, because there is a base rate for every value of the variable. And additivity still applies. Here it looks like minus, but this is actually a plus. Okay? Well, this here it's more clear on this side actually. This is a plus here. So the additivity is the sum of belief masses plus the uncertainty equals 1. That's the additivity. The sum of base rates is just like a sum of probabilities equals 1. And we can compute the projected probability for any value of the variable in the same way. Basically, belief mass of the value multiplied by the base rate of the value plus the product of the base rate of the value plus the uncertainty mass. So it's basically just a simple generalization of the binomial opinion for the multinomial opinions. So in the ternary case, if there are 3 values, possible values of the variable, then it's a tetrahedron. And the point is now inside the tetrahedron somewhere. And in the same way, there is a base rate distribution. So it's a point somewhere on the base triangular plane. And you can draw a line from the top to the base rate point. And you can draw another line from the opinion point in parallel with the director line down to the base plane, and there is the projected probability distribution. So if you really want to have probability distribution, there it is. That is like removing the uncertainty dimension. Then you get the probability distribution. And in general, the equilateral triangle and the equilateral tetrahedron it's a simplex. That's the geometric shape it's called. And simplexes can have any dimensions, but we cannot visualize larger than what's this simplex dimension? 3 or 4? 3. Then you have to close your eyes and imagine dimension 5, 6, 7. But you can still have simplexes of larger dimensions. And you can still sort of imagine that there is a point inside the high dimension simplexes. So high dimension opinions can still be represented in the same way, but not visualized on a flat screen. And similarly to the equivalence between the binomial opinion and the beta probability density function, there is an equivalence between now the multinomial opinion and the Dirichlet. So in the ternary or trinomial opinion case, it becomes a 3-dimensional Dirichlet. So here's the Dirichlet function, don't worry about that. It also has these alpha parameters, the strength parameters, and in the same way the strength parameters of each possible value, the variable. Okay, let's say if you pick a ball, colored balls from an urn, and there are three colors. The strength parameters depends on how many times you picked red or green or white. So the alpha is a function of how many times you picked the different balls, plus the product of the base rate and the non-informative prior rate. And it becomes like a hill shape. That's the hill shape. So this is if you picked, let's say, 3 colors, picked 6 red balls, 1 yellow ball, and 1 black ball. That's what you get. And now the expected probability of the Dirichlet is equal to the projected probability of median. Okay, so they are equivalent. So here's the mapping, bijective mapping between the Dirichlet and the opinions. Yeah, so non-informative prior rate, I explained that already, so I think we just continue. And here is a little comic strip of Dirichlet. So this is before you pick any balls. Let's say you have 3 different balls. How does the Dirichlet look like? And this is it. This is the non-informative Dirichlet. Is it flat? Actually, it's not perfectly flat. Can you see it sort of tips up a little bit at the edges? Oh, can't really see it. Almost. That's because the non-informative prior rate equals 2. In order to make the 3-dimensional Dirichlet perfectly uniform, the W and the non-informative prior rate will have to be equal to 3. But it doesn't make sense to have large values for the non-informative prior rate, because then the prior carries too much weight. Let's say you have 100 different colors in the earth, then you would need to pick, let's say you have 100 different colors, and you pick 50 balls, and they're all the same color. Then after 50 balls, you're pretty sure this urn only contains bloody red balls. That's all I get. Okay, you know that there's only red balls in most of these urns. But if your non-informative prior rate had been equal to 50, you would hardly see any difference in the shape. Okay, so that wouldn't make sense. So therefore, the non-informative prior rate has to be equal to 2 in order to allow new evidence to actually influence the prior. Okay, let's say we pick, we pick 6 red balls, 1 yellow, and 1 black. That's what you get. Pick some more balls, 20 of each. That's what you get. Pick more balls, and you have 50 black balls, and this is what you get. So you see how the Dirichlet shape becomes higher and narrower, more narrow. And after having picked lots of balls, it will be a sharp peak. And now over to hyperopinions. Remember I talked about the median column height? So if balls can be red, green, or white, and I pick some balls and say, oh, I can't see, is this red or is this green? I don't know. So then I assign one observation. It's either red or green. It's an observation. At least I have excluded white. So it's still a useful observation. So now, the belief masses, okay, they apply not just to each specific color, but to composite colors. It's now an allowed value. I can assign belief mass to composite. So there are some balls, they might be red or green, but I don't know which. I have seen some of those balls. I have observed them. So I know in reality they are either red or green, but for me, I don't know. So that's all I can say. So it's still an observation. So now the belief mass distribution is a hyperdistribution. The uncertainty is still the same, and the base rate distribution is still the same. So now we have still additivity between the uncertainty and the belief mass distribution, but now the only difference in the belief mass distribution is that the values of the variable now belong to the reduced power set. Not just the x, but actually the reduced power set. So the composite values, they are now part of this. The base rates, they still just apply to the values of the domain, and we can still compute projected probabilities. It's just a little bit more complicated. Actually, here there's a line there. Relative atomicity is expressed with a vertical line, but you can't see. Yeah, here is a vertical line. So you need to compute. It's not complicated, but we can still compute the projected probability of hyper opinions. And what about the Dirichlet? So now hyper Dirichlet. For those of you who are familiar with Dirichlet, you know, I've shown you some Dirichlets before, and they are basically a hill shape. Hyper Dirichlets, they can be a bridge like this. And they are not very, this is not a traditional Dirichlet. But this represents, you know, if x1 and x1 is red, x2 is green, okay? This looks like there is a bit of evidence on red or green, because that bridge is sort of pushed away towards red or green. But still, there's some evidence of white as well. So this now nicely represents somebody who's colorblind. He doesn't see the difference between red and green, but he can see the difference between white and the two other colors. So his observation would then be like green, and his hyper Dirichlet would be represented by the bridge. So the opinions through these bijective mappings between binomial, multinomial, or hyper opinions to beta probability density functions, Dirichlets or hyper Dirichlets. So opinions are firmly anchored in traditional statistics. Okay, this is not a weird abstract theory which doesn't connect to anything. This is firmly anchored in statistical theory. And another relevant formalism is fuzzy logic. Now, is this the same thing as fuzzy logic? Maybe it is, maybe not. Fuzzy logic has this notion of fuzzy membership functions. Like you can have tall person, average person, or small person, which are like fuzzy concepts. And they can be slightly overlapping. But you can actually measure persons exactly to the last millimeter. So this is a sharp measure. So from the sharp measure, you have a membership into some fuzzy concepts like tall, medium, or small. How about subjective logic? the domain of subjective logic is supposed to be crisp. Now, the coin is either heads or tail, the ball is either red or black. There is no overlap of slightly red, slightly green. No, it's crisp. Whereas the measures about the domain is fuzzy. You can say, I don't know. It's hard to measure. So, therefore, fuzzy logic and subjective logic are kind of diagonally opposite. Fuzzy logic has crisp measures, like millimeters of persons. How tall are you? Subjective logic has vague, uncertain measures. Fuzzy logic has fuzzy categories. Subjective logic has crisp categories. So you see, they're not the same. They're quite different. I guess you could express crisp measures also in subjective logic terms. So it will be possible to combine those two formalisms somehow. So that will be an interesting, I guess, research paper. Okay, so how's the time going? So another hour almost, isn't it? Another 15 minutes. Okay, so what can we do with these opinions? We can use them as arguments in operators. I've already mentioned the correspondence between binary logic and probabilistic logic. So if we generalize even more, then we get subjective logic. So there is this generalization from binary logic to probabilistic logic. And then it becomes a homomorphism if in the binary logic you only consider probability equals 1 or 0. If you exclude any other probability, you say only allowed to have probability 0 or 1, then probabilistic logic becomes binary logic. It's the same thing. You can generalize probabilistic logic to subjective logic by including uncertainty, the uncertainty dimension. But then if you exclude all opinions with some uncertainty, you say uncertainty mass has to be 0 always. No uncertainty. Then every opinion is basically a probability distribution. So then it becomes a homomorphism from subjective logic to probabilistic logic. So this homomorphism is expressed like this. If you take the projected probability of the product of two opinions, it's equal to the product of the projected probabilities of each opinion. Similarly to, if you only allow absolute opinions, that's opinions which are in the right-hand corner of the triangle, or in the left-hand corner of the triangle, they are equivalent to false or true. Boolean false or true. Then the Boolean value of the AND function is equal to the AND function of the Boolean values. So this is homomorphic correspondence. And here are a couple of tables showing the various operators of subjective logic. Of course, you can do addition, subtraction, complement, projective probability, multiplication, division, co-multiplication, which corresponds to OR. So division is actually in binary logic. There is no division. An AND would that be? But you can always construct a binary logic operator, which is an AND. Of course, it doesn't work if the divisor is false. It's like dividing by 0. So the truth table of an AND would have a not defined in case the divisor is false. And you can have co-division, which then will be un-or. And some more fancy operators. In trust, there is transitivity. I trust you, you trust somebody else, and you can comment on it. There is fusion. Multiple agents have separate opinions about the same thing, and they can then fuse their opinions. Various types of fusion, cumulative, average, constraint. And then there is conditionals and the inversion of conditionals. And this is then equivalent to Bayes' theorem. And actually, in binary logic, there is this notion of contraposition. For those who are familiar with discrete mathematics, contraposition, what's that? X implies Y is equivalent to not Y implies not X. That's contraposition. So this is like inverting, because X implies Y, and then you switch them around, you have Y something X, which is basically Bayes' theorem, because you flip things around. So that's Bayes' theorem, and then deduction, and then abduction. I'll explain in a minute what the difference is. So now, let's look at trust networks. And here's a typical example, or I think it is a typical example. Bob, he has used a garage where the car mechanic Eric works, and he has been perfectly satisfied with Eric's services every time. The car is always shiny and engine is in perfect order. So, because based on experience, direct experience, Bob trusts the car mechanic. Here comes Alice. She's new in town, a new colleague of Bob in the office, and she needs her car fixed. And she doesn't know where she should send her car. So she asks Bob, and Bob, maybe Alice has seen Bob's car and it looks well maintained, and Bob looks like a reliable person, so she trusts Bob in matters of providing advice about where to fix the car. And she doesn't trust Bob to actually fix the car. He might just be a computer nerd, or an accountant, but she trusts Bob in order to provide some advice. And let's say Bob gives some advice to Alice about Eric. Based on Bob's advice, Alice can now derive trust in Eric, magic. This is transitive trust. And you see, I've given some specific names. I call them direct, functional trust. Direct because Bob has some direct experience, and functional because Eric is actually going to fix the car. He will do the job. Alice's trust in Bob might be direct because she has actually seen Bob's car and she knows Bob, so she has direct experience about Bob and his car. But Bob is not going to fix the car. He will only refer to somebody else. So therefore this is referral trust. It's not functional trust. What about Alice's trust in now the car mechanic Eric? She has never seen Eric before, has never had her car fixed at Eric's garage. So her trust in Eric is indirect. But Eric is going to fix the car. He's the mechanic. So the trust is functional. So you see the combinations between direct and indirect, functional and referral trust. And this is actually important. So, in a transitive chain like this, let's say Bob says, actually, I don't know a car mechanic, but I know Claire, you know, she knows a car mechanic. You can imagine that kind of serial recommendations. The last edge must be functional. And all the other edges must be referable. So this is like a semantic constraint for a transitive chain to be valid. And I just want to mention here that the last edge doesn't have to be trust. It can simply be an opinion about something. Some variable X. You think it's going to rain tomorrow? You think it's going to win the European football championship or whatever? It doesn't have to be trust. We'll get back to that. So let's say Claire provides some advice to Bob. Bob provides advice to Alice, and then Alice can derive functional trust. Not referral trust, but functional trust. So, let's say each of these relationships, let's say trust, they can be expressed with some kind of opinion. Then the derived trust is diluted. I call it diluted. It's not weaker, it is more uncertain. Okay, that's what it is. It has higher uncertainty, less confident, that's what it is. And there is a graph notation for that. And there is a subjective logic computational notation. So, let's say just take the last one. Omega superscript C subscript E. The last one. Omega C E. What's that? That's Claire. That's Claire's opinion about Eric. So Claire at the top, the superscript, and Eric at the bottom, the target. So source and target for one particular edge. So here there are three edges: Alice, Bob, Bob, Claire, Claire, Eric. So here there are three opinions: Alice, Bob, Bob, Claire, Claire, Eric. And the operator is actually the discounting operator, because Claire's advice to Bob and Bob's advice to Alice is discounted as a function of how much trust Alice puts in Bob, how much trust Bob puts in Claire. Let's say Alice gives an advice to Bob, but Bob doesn't trust it. No, sorry. Claire gives an advice to Bob. Claire gives an advice to Bob, but Bob doesn't trust Claire. She simply discounts. He discounts whatever she says. So if somebody who you don't trust gives you an advice, what are you going to do with that advice? Ignore it. Okay? It's a worthless piece of advice because you don't trust the source. So therefore, it's trust discount. You discount as a function of how much you trust the advisor. And here comes fusion, trust fusion. So now let's say Alice, she asks Bob, and Bob says, actually I don't know a car mechanic, but my friend David, he knows a car mechanic. And Alice is not happy, so she asks Claire, Claire, do you know a car mechanic? And she says the same thing, well actually all I know is David. So if David and Bob give some advice to Alice, and also through the other path, so you can have this kind of, this becomes a trust network. Alice can still derive a level of trust in Eric through this network. And the formula is just a little bit more longer. So let's have a look. The computational trust expression at the bottom. We have Alice's trust in Bob. That's omega AB. You see that? Omega AB. Alice's trust in Bob. And Bob's trust in David, that's omega PD. So that's this edge from Alice to David. And now the other edge, from Alice via Claire to David, that's the next term, omega AC, omega CD. So you have two parallel paths, two terms. And here comes the circle plus. That's the fusion operator. So now these two terms can be fused. So that's the whole diamond-shaped network. Okay, so the fusion of those two terms is the circle plus. And then comes the last edge, which is David's trust hierarchy, which is now a trust discount operator, which comes at the end. So you see, this is a trust algebra, and it can be computed. So with discounting, I already said this produces diluted trust, less confident trust. But if then we add parallel paths, then the confidence increases. So you have a long path, confidence goes down. You add more paths, confidence goes up. Okay, so more information. But beware, there are two ways of passing advice. Let's say David provides some advice to Bob and Claire. This allows Bob and Claire to derive trust in some statement X. This is not car mechanic Eric, but let's say, I don't know, Germany will win the football championship or something like that. And now it's possible that Bob and Claire provide their opinion about X directly to Alice, like this. So Alice can derive a level of trust in X. This seems to make sense, doesn't it? But actually this is not good. What's wrong? Because Alice now ignores David. He was part of the whole trust network. But Alice now ignores David. So that is what she perceives the trust network to be. It's a trust network without David. But if she computes it, this is what she actually computes. And observe dx. Now this trust edge here appears twice. You don't want to take two pieces, the same piece of evidence into account twice. So this is what Alice perceives the network to be on the left-hand side. This is the network. But if she computes it, this is actually what she computes. It is as if David has been deduplicated. Not good. So, the only way to do this correctly is that all the evidence, that all the pieces of advice must be passed either directly to Alice or in an unchanged form. It can very well pass via Bob and Claire, doesn't matter, but Bob and Claire should not change them. They should arrive unchanged at Alice. So that now Alice has full overview of the whole trust network, and then she can actually derive the correct, compute the correct trust without any unknown dependence in the network. Oops, that was a bit quick. And this is an attempt to visualize trust discounting. Here is Alice's trusted Bob. Let's say we have the network Alice, Bob, and Bob X. Bob to not car mechanic, but to some variable X. And here's an opinion point. So this represents Alice's trusted Bob. This opinion represents Bob's opinion about X. And X can be the weather, who's going to win the football game, or whatever. And Bob can give some advice to Alice about X. And this is the derived opinion, Alice's derived opinion about X. Okay, so on the right-hand side. So what's going on here? You can see it is like there is a sub-triangle. Okay, sub-triangle at the top. Here is a sub-triangle. The size of the sub-triangle at the top is determined by the projected probability of Alice's trust interval. That's what a P, A, projected probability A. That means if Alice distrusts Bob, the projected trust probability will be 0. Okay, 0. If Alice distrusts Bob. That means that the size of the subtriangle will be reduced to 1 point at the very top of the triangle, which means completeness. That is, Bob gives a piece of advice to Alice. For Alice, it is worthless. So she is completely ignorant about variable x. So a piece of advice doesn't tell her anything. So then the blue opinion point is then basically linearly mapped from Bob's opinion about x, that's his advice, to the same position linearly inside the subtriangle. So if the subtriangle is reduced to a point, the point inside the point is still a point, which is at the top of the triangle, which is a vacuous opinion, which means I don't know. That means if you don't trust somebody, their advice is worthless. But of course, if Alice has full trust in Bob, then the subtriangle is equal to the whole triangle, and then basically this point will have the same position in the rightmost triangle. Same position. That means whatever Bob says, Alice will fully believe exactly what Bob says. It is the same thing. So that's how you can compute. This is computational trust. And one possible application could be like a court case. Let's say there is a question about the accused. Where was he at a specific time? At the location of was he actually at the location of the crime? And 3 witnesses, it was 1, 2, 3. They say, I saw him. I think he was there. And another one says, I heard him. I heard his voice. So I think he was there. And the third one says, I saw his car, so he must have been there. And then the judge has then, or maybe one of the witnesses says, no, actually he was at my house, we had a party, and he was at my house, we were drinking, and he wasn't at the other place, he was at my house. So the judge now gets conflicting opinions about the statement, where was the accused at the given time. Now the judge needs to fuse all these possibly conflicting opinions. And let's say one of the witnesses is a drug addict or alcoholic. So the judge says, oh, I don't trust his testimony that much. Whereas another one can be academic, research with artificial intelligence, highly reliable person. So the judge says, yes, I take your testimony into account with a high weight. So that's what the judge does. That's what we do. We take different pieces of advice into account by giving them more or less weight. And this can be perfectly done in subjective logic through fusion. So I'm going to show some operators then about fusion and trust transitivity. Okay, so here are 2 arguments, to the left and in the middle, and then the result is on the right hand side. So I'll list. Yeah, this is the scamping. Okay, that works. So let's say Alice distrusts Bob. Bob can say whatever he wants. Doesn't matter. It is worthless. Alice. So the Alice's belief in the target statement, X, let's say, is still useless. If Alice has full trust in Bob, then what Bob tells Alice, Alice will believe it perfectly. So now there's a perfect mapping now from what Bob says to what Alice derives. And then you can have something in the middle, okay, so then there's not a perfect mapping. So you see that now there's a sub-triangle has been reduced. So if I move the Bob's advice around the triangle, you see now this becomes a sub-triangle in Alice's derived opinion. This is what I understand. So that's the trust discounting operator. What about fusion? Fuse. This is cumulative fusion. So here are, let's say, two witnesses giving evidence about some statement. And if so, this doesn't take into account trust discounting. Okay, so let's just assume the judge weighs the two testimonies exactly the same, okay, without any discounting. So if they both say yes, we saw the guy, we saw the accused at the place. So if we have a slightly uncertain opinion there and a slightly uncertain opinion there, you see the fused opinion has higher confidence. That means it is closer to the baseline. That means higher confidence. If one of the witnesses said, I don't know, I never saw him, I never heard him, I wasn't there, so I don't know why you invited me as a witness. I have nothing to say. Okay, so then the judge needs to only take the other witness. So then whatever the other witness says is that's what the judge thinks. But of course, what if one says, yeah, I saw the accused, he was there, and the other one says, no, he was at my house, we were having a party. Okay, so then you see, then the judge doesn't know what to think. And here we come back to the question of frequentist or subjective opinions. So the result here is frequentist. You see, because it's more confident. But another fusion operator is the epistemic fusion. That means, let's say in the Oslo case, one witness says, yes, I was there, I saw Oslo shoot Kennedy. Oh great, then we know he did it. But then comes another one that says, no, I was actually sitting in the police car behind Kennedy, and one of the security guards stumbled, and his gun fired. And that's what killed Kennedy. Now somebody claims that actually. But then we don't know, because we have two testimonies and they say different things. So then it is these two kind of testimonies cancel each other out. It doesn't produce a frequentist opinion about who killed Kennedy. This is a bit philosophical. So if you say this is not a frequentist case, then this conclusion should actually be a vacuum. Okay, that's another possibility. Okay, and let's now make the trust network. Here we have all the participants, Alice, Bob, Claire, and David. And let's say Alice trusts Bob. If Alice totally trusts Bob, and here's Bob's advice to Alice, then because Alice fully trusts Bob with absolute trust, whatever Bob says, Alice will believe it. Even though, let's say, Alice has a slightly uncertain opinion, Bob will believe it. Okay, that's another possibility. So this is Alice is just in Claire. Claire can now say whatever she wants, doesn't it? What's this? I didn't read this one. Yeah, that's right. Okay, because it's only if. Also, Bob says this is true, then it doesn't matter what Claire says. But now, Bob doesn't give an absolute opinion about or an absolute trust in David. So then both paths, these are now two parallel trust paths, both matter. So this operation now combines both trust discounting as well as trust fusion. So the two operators are true. So now this is how computational trust works. You combine the concept of transitivity through trust discounting and fusion, trust fusion. And there isn't just one fusion operator. There can be many fusion operators. Yes?
So what if average just pop into there 100%? They may have
Then the world comes to an end. Of course, you can have the extreme case when there is full trust in one path, and then the other path says the complete opposite. Of course, then you don't have a solution. I think my computer is going to break down. No, I'm just joking. Let's see what happens. Full trust. Okay, so it's got to be here, full trust. Oops. And this trust, okay. Oh, it's 0.5 probability. Easy. It worked. It didn't break down. So it works. There is a solution to that. In the belief theory community, there's a lot of confusion about fusion. All they talk about in every conference is fusion. Because they can never agree about whether Dempsey's fusion rule works or doesn't work. And there is nothing wrong with Dempsey's rule, but it only applies to a specific situation. And what they typically ignore is that there are many different types of fusion situations, and each different situation requires a different fusion operator. Simple as that. I'm not going to post it, but there are different fusion operators. Now over to Bayesian reasoning. And this is typically conditional reasoning. You know, there is causality, there is some state variable, let's say the state of rain or sunny weather, and another variable, somebody carries an umbrella out. So typically, the state of rain will cause people to carry an umbrella. But carrying an umbrella doesn't cause rain. Maybe some people think that. I don't think it works. So there is causality between rain and umbrellas. The causality, of course, I think there was in a previous talk, isn't obvious. But let's say you have two lamps connected to the same light switch, and you see one lamp being lit. You can deduce, oh, the other lamp must also be lit. But the first lamp didn't cause the other to be lit, and the other lamp didn't cause the first to be lit. They're caused by something else. They had a common cause. Okay, so reasoning from a parent variable, cause, to a child variable, consequence, is deduction. But sometimes we want to reason the other way around. For example, you see somebody carrying an umbrella, you know you're in a hobby You're inside the hotel, you haven't looked out the window, and suddenly you see everybody carrying umbrellas. You say, oh, it must be raining outside, because I see all these people with their umbrellas. So this is abductive reasoning. We do that all the time, and we don't really even think about it, but it's actually abduction. And so this is kind of simple abduction because you know the variable. But let's say you have the habit of locking your door every time you leave in the morning when you go to work, like most people do. But one evening you come home and the door is unlocked. And then you start thinking, how did that happen? Maybe I forgot to lock the door this morning, or maybe there was a burglar, or you start to look for possible causes, hypotheses, and you try to assign probabilities to the various hypotheses. This is really what people call abductive reasoning, trying to find the causes. But I also call abduction trying to assign opinions or probabilities to those causes. It's also abductive reasoning. So now, observing umbrellas, and then assigning or finding the cause, it must be raining, or maybe there's an fancy umbrella competition. That's another hypothesis. It's not raining, but they're all going to their fancy umbrella competition to see who has the fanciest looking umbrella. It's another hypothesis. And deduction then. There are conditions for deduction. And now we have these triangles and tetrahedrons again. And in a ternary variables, for three possible values, there are three conditionals. Probability of y given x1, probability of y given x2, probability of y given x3. So you need to have three conditionals. So these three conditionals now define the corners of the subtetrahedron. See, there are two tetrahedrons, left and right, and inside the right one there is a subtetrahedron. And the subtetrahedron has three corners at the base. These three corners are the conditionals. That means if I know the value of variable x to be x1, okay? If I know the variable x to be x1, then I know that I have an opinion, or you can call it probability of y. That's actually this corner here. If the value of x is x2, then I know it's that corner over there. If its value of x is x3, then it's this corner over there. So x1 corresponds to this y value, and x2 corresponds to this y actual opinion, and x3 corresponds to this y opinion. There are three opinions, one for each corner. And then, of course, if you are completely ignorant about x, that is the apex opinion in this subtetrahedron. Vacuous opinion on x corresponds to this apex opinion in the subtetrahedron. It's all geometry. Of course, this subtetrahedron doesn't have, this is perfectly symmetrical shape, but it can be any twisted shape, okay? It doesn't have to be that nice, it can be twisted upside down, or not upside down, but it can be sort of squeezed, it could be a squeezed shape. But now, deduction is extremely simple. It's just a question of linearly mapping this opinion point in the x tetrahedron to the same linear equivalent position inside the subtetrahedron. Okay? From this point, a linear mapping to the same position inside the subtetrahedron. Simple as that. So you should think about what is this? This is deduction with opinions. And this is actually deduction with Dirichlet probability density functions. There is no simple analytic way of doing this with Dirichlet. If you try, get into hybrid geometric functions, and it becomes a completeness. So it's intractable. Theoretically, you might be able to do it, but basically it's intractable to do it. So how come this is so simple? With subjective logic, is there something wrong with this? Well, I wouldn't say something wrong, but this is an approximation. Just beware of that. Because in subjective logic, all the arguments are opinions, and every result is also an opinion. And every opinion is either a beta or it's a Dirichlet probability distribution. So everything is Dirichlet or beta. That's all there is. I just mentioned, if you try to do this mathematically with Dirichlets, you get hypergeometric functions. And a hypergeometric function is not a Dirichlet. So, if the result here is a Dirichlet, then it is certainly not a hypergeometric function in general. So, subjective opinions of these computations approximate what otherwise might be a something complex hypergeometric function to a Dirichlet, a nice Dirichlet. So, what is the approximation? Well, the first moment, that is the projected probabilities, they are the same, always. The variance, that's where the approximation is. So the variance of opinions, they also have a variance, an opinion has a variance, is not exactly the same as the variance, the analytically correct variance, as the analytically correct variance of, if you try to do this with the Dirichlet functions. So that's just the difference. Okay, I'm just going to try a little demonstration. Deduction. So let's say this is the rain and umbrellas. So let's say if it rains, I usually carry an umbrella. If it doesn't rain, I usually do not carry an umbrella. Okay. And here, does it rain or not? Let's say today it rains. You can already predict an opinion about whether I carry an umbrella or not. It's actually the same as this one here. If it doesn't rain, you can already predict whether I'm carrying an umbrella or not. It's this one here. And now, you don't know whether it's going to rain or not. You haven't watched the weather forecast and you haven't seen out the window. So what's your opinion about me carrying an umbrella or not? Well, you don't know. So it's this point here. So now you have still a predicted probability, but your confidence is low. Let's try abduction. It's a little bit more complicated. Let's do another example, a medical test. For medical tests, the pharmaceutical companies, they need to determine the reliability of the test. So they take 100 persons with the condition, the disease or the infection, and they see how many times is the test positive. Okay, here. True positive rate. Here we go. Not maybe it was not always positive, even though the person was infected. And then we take 100 non-infected persons, and you see how many times the test was positive. So that's the false positive rate. So most of the time the test was negative, but maybe sometimes it was positive. No test is perfect. And here is now the outcome of the test. And the question is the person infected or not? So let's say the test is positive, and it looks like the person is infected. Let's say the test is negative, and it looks like the person is not infected. And if you don't know, let's say you can't actually see the test outcome. Maybe the test outcome is the color of some paper strip, and the doctor is colorblind, so they actually can't see whether it's red or green. Then, of course, he says, I can't see the result of the test either. But now the problem is the base rate fallacy. That means if you test for a condition which is extremely rare, which hardly exists, like tuberculosis. So this is the base rate of the this is the base rate of the condition, let's say tuberculosis. Let's say the test is positive. You have a positive test, and it looks like you're infected. But if you test for a very rare disease, you see how the base rate causes the conclusion to be more and more uncertain, less and less confident. And also the projected probability to go down. And eventually, even though the test is positive, the conclusion is you don't have the disease. I'll give you an extreme example. Let's say I take a pregnancy test, and it's positive. That's possible. Maybe I have a weird hormone disease. Should the doctor tell me that I'm pregnant? Well, the doctor said that given the base rate of male pregnancy is 0, even though the test is positive, you are not pregnant. So this is the how you see that. So when you need to, in traditional probabilities, you apply Bayes' theorem for this. And the thing is, you don't see the uncertainty in Bayes' theorem. All you see is the probability. Whereas, with subjective logic, if you have these different opinions about the conditions, you clearly see how the uncertainty or how the conclusion can become very, very unconfident, or they're highly uncertain. So this is really a value of probability of subjective logic over probabilities, that it clearly expresses the level of uncertainty in conclusions that you otherwise don't see. It is known that Bayes' theorem can produce very unreliable results. So, for example, if the two conditionals are quite close, you see how the conclusion is completely uncertain. Whereas in the projected probability, now that's this blue line, if you only use probabilities, you are blind, completely blind to the uncertainty, and you don't see, you might think, oh, this is a good reliable probability, but actually it's completely uncertain and completely unreliable. So Bayes' theorem like this, I'm not going to talk too much about that. So there is the subjective Bayes' theorem. So the Bayes' theorem generalized to opinions. So it's not so easy. In the binomial case, okay, so we have two conditionals, y given x, y given not x. We also need the base rate of x. And then we can compute opinion about x given y and x given not y. So this is the binomial case. For multinomial, we say just generalization. Given that we have a set of conditionals, y given x1, y given x2, y given x3, etc., depending on how many possible values you have, and the base rate or the prior probability distribution over x, it's possible to derive a set of conditionals, x given y1, x given y2, x given y3, etc. So And with this, you can do this kind of computation I showed you in the binomial case. Yeah, so it's like inversion. So let's say the conditionals are defined like this. Okay, so it's a subtetrahedron inside the other tetrahedron. What you do when you apply Bayes' theorem is turn it around. So you create a subtetrahedron in the x inside the x tetrahedron instead of inside. So you go from y to x instead of from x to y. So that's what Bayes' theorem actually does. So you can visualize what it does. So the computation is expressed like this, but of course the mathematics, basically it's simple algebraic formulas, nothing complicated, and the computation is extremely fast. So you can do deduction, it's expressed like this, or abduction, expressed like this. Medical reasoning, that's what I just explained. Abduction, I also explained. And now, during this talk, I first described trust networks. Okay, so Alice, Bob trusts Eric, etc., etc. And then I talked about Bayesian reasoning, variables, x, y, and z, things like that. Now let's combine those two concepts, trust networks and the Bayesian networks. So if you combine Bayesian networks with subjective logic, so instead of having just Bayes' theorem, we have subjective Bayes' theorem to do the same thing. So that becomes subjective Bayesian networks. And then we can combine it with subjective trust networks, basically trust networks, computational trust networks. And then this becomes subjective networks. So this is an example, okay? Here we have a little Bayesian network at the bottom. There is a conditional relationship between variable x and variable y, and between variable y and variable z. So it's a very simple Bayesian network. And here we have some agents. A, that's the analyst, let's say, and A gets some advice from B, and B knows something about x. C also knows something about x. Okay, here. B knows something about variable x, C knows something about variable x. And they both provide advice to the analyst A. So A has two pieces of advice about x. A needs to apply trust transitivity and fusion to know something about x. Maybe A knows something about the conditional between x and y, and A knows something about the conditional between y and z, and maybe A has a conditional, knows something about z, etc. So now A has, through various agents, information about the variables. So first, A applies trust transitivity and trust fusion, and then can analyze the Bayesian network. So this is a visualization then of what it is. It's actually two different networks. There is the subjective trust network to derive opinions about the variables and about the conditionals. And then there is the subjective Bayesian network to actually analyze the Bayesian. And together, this is the subjective networks. And we actually have a couple of projects about this topic at Oslo University. One of them is actually funded by the US Army Research Labs. They work on intelligence analysis, and these are models that they find useful for actually intelligence analysis. They get information from various sources, sometimes unreliable and maybe deceptive sources. So they need to apply trust networks to assess the reliability of evidence from these sources. And then they can then apply what they know about various variables to derive some conclusion about various things. Typically, military intelligence is applied to. And there will be a book coming out very soon. And unfortunately, it's always a bit late, so I didn't get the book in time. But I have a few copies actually. 1, 2, 3, 4, 5, 6, 7. Just I just printed out and bound. But there are more than 7 of you here. But let's just try. How many are interested in having a copy of the draft book? Hands up. 1, 2, 3, 4, 5, 6, 7. I think you were number 8, were you? Or okay. All the guys put the hands up. But yeah, but if there are only 7 you really want the book, then it's okay. Number 8, yeah, okay. Okay, so then we have to have a look at it. So Jan, please.
I'm writing down a number between 1 and 8, and you all say a number, and one who guess the number doesn't get it. Okay? Between 1 and 8. Okay.
So all of you who raised your hands, you're in the game.
Number between 1 and 8. 1? No. No.
7.
No. 5. No.
6.
4. 4. Sorry. You win the lottery, but you don't win the book.
Okay, you others, come and grab a draft book. But I have a flyer from Hollywood, so you can, when it comes out, order it from Springer. This is just an information about something. That's the end of the presentation, so you can go again.